should help clarify some of your work, or at least help support some of your work in just now in the pivot activity. When a conducting rod moves perpendicular to a uniform magnetic field in this sort of loop orientation, such that we are changing the area of the loop, there is an EMF induced associated with the motion through the magnetic field. And that's exactly what we are examining here. The conductor length is L, which if we're talking about our wire loop in the pivot activity, we could have called that maybe the height of the loop, because it stands up from the glider. But essentially it's the length of that conductive piece that's moving through the thing. And VBL, if there's only one loop. If there's more than one loop, then we should use we should count the loops and include a parameter for that as well. And I suspect that's very much the formula that you ended up with, NBLV. So if that's a formula, either BLV or I guess VBL, it's all commutative. If that's a formula you ended up with, then you were in good shape. Just remember that if we have multiple loops, each loop is seeing the magnetic flux change, and each of those loops is going to see its own EMF, and there are 8 of them, so we have to multiply by 8, or however many there are, we have to multiply by n. At this point, having shown you this, what questions do we have about the pivot activity?
Do you want us to finish it if we haven't finished it yet?
Eventually, yeah.
Yeah. Okay.
But right now, I'd like to just, if folks have questions, then I want to get them answered. But if it's just a matter of I still have to finish it, I'd like us to wait for that until after we talk about a couple more things.
Okay, no problem. Thank you.
Thank you. And I'm just cool. I'm just pulling up the PowerPoint on a different device here so I can look ahead and see what see what's coming. We talked about before we sort of went into breakout rooms to talk about the to do the pivot. We were talking about at the end of the video example, the video tutor example, we were talking about how these are fundamentally different electric fields than the electric fields that have to do with static charge distributions. This kind of magnetic field does not do zero network in a closed path. The EMF, now we used to, right, talk about EMF or any potential difference as a path integral E dot dl. But that was like way back when we were talking about the electric field between capacitor plates. And we said that the potential difference has to do with, V equals, or delta V was equal to, I think, the negative of the integral E dot dl. It was the E and the path we walked were parallel, so it was just the product, and it was ED. But the calculus behind that was E dot DL, which is a path integral. Now, it's interesting that we're using a path integral because we talked about, as far as Ampere's law goes on Tuesday, we talked about the circulation of a magnetic field having to do with the current enclosed by the loop of the integration path. But the circulation is apparently part of the story for magnetic fields. And here we're talking about an electric field that is circular. Such that we could talk about its circulation as well. We could talk about the total path integral E dot DL around the circle, around the closed loop that we're talking about. And we would end up with the potential difference associated with the current in that loop, which is the EMF that we're looking at. It's the EMF in Faraday's law. So where we've got EMF, we could replace that with a circulation calculation. There has to be an electric field in the wire if there is to be a current. That's got to have it. So we can sort of explicitly include that electric field if we talk about the circulation or the path integral in a closed path. The loop, the path of the current, in other words, the wire loop. What is this diagram showing? All right, so we've got a coil, a solenoid here, right? And we've got a wire loop with a galvanometer attached to it. If we change the magnetic field that passes through the area of that loop, then we change the flux experienced by the loop. And if we change the flux experienced by the loop, then there is an electric field. There is an EMF according to Faraday's law. But here I'm saying, if we express that as the path integral in the loop of the electric field, we can modify Faraday's law that way. Note the explicit inclusion that this has to be a stationary integration path. This can't be a dynamic thing. The integration path can't be moving, so it might not be useful for this situation, because here we've got a path that is not stationary. Its area is changing. Now, in the pivot activity, the integration path is the wire loop. Just because there's only magnetic field in a particular section of it, well, that's like what we're saying here. There's a wire loop of a particular size, but only some area of it is actually, experiencing magnetic flux. That's fine, as long as the wire loop in question is stationary. It seems useful at this point to briefly discuss applications, and sort of the go-to application for the small currents that are induced in macroscopic objects that are conductors at all, have some conductivity, we can detect those currents and use that to detect these materials in which currents are induced. In other words, we can detect metals. The metal detectors at airport checkpoints are induction meters. We've got transmitting coils and receiving coils, and if we turn on the as we walk through the metal detector, that's motional EMF. We're moving a conductor through a magnetic field. If there is some metal in this person's briefcase, we could that way induce a current to flow in that metal. That current has its own magnetic field associated with it, and that means that the field as observed by the receiving coil has changed. It experiences a change in flux. And so it sees a current, and if we see a current in the receiving coil, then we know that there is metal present. I'm going to skip a couple of slides for now. I'm going to go back to them. In 1820, we said, Ørsted publishes his findings of the magnetic field produced by a current carrying wire. And the associated fields of electricity and magnetism explode with research. Within weeks, BO and Savart make their measurements. Within 10 years, Faraday makes, and a couple other people, notably Henry, make their measurements of electromagnetic induction, and that's what we're talking about here. Within another 50 years, basically, everything we know about electricity and magnetism was discovered by, I don't know, like 3,000 different people, and all in different places. James Clerk Maxwell got a bunch of publications and a bunch of paper and retired to a cabin in the woods for like 3 months. And he emerged from the cabin later, probably rocking some kind of righteous physics beard, having sort of isolated 24 or so, maybe 20 different equations that were the entirety of everything that was currently known about electricity and magnetism. A monumental effort to sort of collect all of these different pieces. Faraday, see, the interesting thing about Faraday's work is that Faraday was not a mathematician. He had all of the like mountains of observational data about induction, but did he write it with EMF equals negative derivative of flux? No, he did not. We can credit Maxwell with starting the process of formally sort of codifying what was collectively known about these phenomena. Even Maxwell's description of it was complex. There were 20 different equations, and they weren't necessarily all that elegant, but it was Maxwell that started this work. And so we give credit to Maxwell here, even though it's actually I'm really excited about Oliver Heaviside, who did the bulk of the work to distill those 20 or so equations into 4. That with these 4 equations, we can say everything we need to say about the whole thing. Gauss's law for electric fields and for magnetic fields. Gauss's law talks about how is it that charges manifest magnetic fields. How does that look like? It's Gauss's law. Coulomb's law is packaged within Gauss's law. We don't need Coulomb's law. It's here. There's no such thing as a magnetic monopole. Let's say that with Gauss's law for magnetic field. The total flux through a closed surface, the total magnetic flux through a closed surface is 0. Okay, how is it that a magnetic field is produced by its sources? Well, its sources, this is Ampere's law from Tuesday. If a surface bounded by a loop contains, well, is pierced by current flowing, then the magnetic field exists and we can quantify its circulation. That's the 4th equation. The 3rd one is Faraday's law. And we might as well use there's no sense introducing another variable. We can be more elegant than that. We can just talk about electric magnetic fields, electric charge, and electric currents. And we can tell the whole story. So fucking cool. So cool. That these 4 things, and that's everything we could ever say about electromagnetism. And it's at this point that we start to say electromagnetism, because it's clear that these are related phenomena. The one affects the other. Electric currents create magnetic fields. Changing magnetic fields create electric currents. Like these are sides of a coin. What happened though to Ampere's law? It looks different now. It didn't used to include this funky looking jazz. It used to just be permeability mu sub 0 times I, the current enclosed. What is that other junk? That's a good question. And this is why I think we're going to name these 4 equations, even though it's the product of Heaviside's work to sort of rewrite and rewrite and rewrite Maxwell's equations in the sort of vectorized calculus formalism that we're seeing them written in. It's Maxwell's understanding that there is a logical inconsistency in Ampere's law as we wrote it. And his insistence, Maxwell, I mean, that this inconsistency needs to be resolved if a coherent statement of electromagnetism is to be made by any number of equations, whether it's 20 or 4. The term that we're discussing, this one, had never been measured, had never been observed, and with the equipment available in the 1880s, would not be observed for some years. But Maxwell was convinced that this term needed to exist in order to fully describe what's going on. That thing is the key, that term is the key to our current understanding of light. Back in 231, we talk about Newton's synthesis, the idea that terrestrial gravity and celestial orbits are governed by the same relationship, that we can synthesize what was entirely different science. That was, you need a telescope and star charts, and this was, okay, I can measure it, I can drop a thing and I can see it fall. I can use a spring and measure a force, empirically. That I can only sort of observe. I mean, I guess it is empirical, but I can't experiment with it. I can only observe it. And they were fundamentally different areas of inquiry until Newton's synthesis, until he was able to show that with the one law of gravitation, he could explain terrestrial motion and Kepler's laws of celestial motion. This thing that we're talking about here, the collection and sort of codification of Maxwell's pile of equations, we could call Maxwell's synthesis. And it is certainly equally important. Just the synthesis on its own, being able to, after a little while, after some work from Heaviside, being able to express the entirety of the known about these phenomena with 4 equations. How fucking cool is that? But so that, I guess, is Maxwell's synthesis, but Maxwell goes one better. He fixes Ampere's law with a term that is not observable because it has to be there, because symmetry, because it just needs to be there. I have an argument for why it needs to be there, but I'm talking about the symmetry because it really was like, we talked on Tuesday about the fact that Ørsted had a fundamental belief in the unity of forces. Maxwell is right there with him, that this needs to feel right in addition to being right. It wants to be elegant. And it is the elegance of these 4 equations, especially if we write them using the vector calculus operators that we've been working a little bit with, the divergence and the curl, which we'll get to that. The simplicity of expression of these sort of myriad ideas is what drove Einstein to conceive of relativity. So you looked at these equations and you said, equations this beautiful have to be right. There's just something about them. And to make them consistent with all motion, that's what kind of guided him to special relativity and then general relativity. Like that was the motivation, is these equations. I can't get over. I can't get over it. Ampere's law written this way, yeah, it's cool, but it's so much cooler if we write it using the local field equations, the divergence and the curl, the vector operations. So we are going to cover that, not today, but we are going to rewrite these equations in the vector calculus that we've been developing, because I just think it's fucking worth it. We're this close to curl as a vector operator, and it does y'all a disservice if I don't like at least show it, you know? So cool. All right, so where does that really, really special term that the professor is so excited about, where does that come from? It's a little bit of a contrived problem, but it is in fact a problem. Consider two surfaces. One is a planar surface, a circular surface that is pierced by the current in a wire that is charging a capacitor. There's a battery somewhere in the circuit. The circular path around that circular surface shows non-zero circulation because it's pierced by a current. Ampere's law says, okay, B dot dl, integrate, you get mu times I sub c, the current passing to the capacitor. But that isn't the only surface we could draw that uses the same circular loop. Ampere's law says absolutely nothing about which surface to draw. It's like Gauss's law. It doesn't matter whether we draw a sphere or a cylinder or some other shape, as long as it's a closed surface, it doesn't matter. So we could sort of imagine like a bubble wand. We could sort of bulge that surface out to include so that it passes to the right of the positive capacitor plate, which means there is no wire carrying current that passes through this soap bubble surface. This outer surface here does not have a current passing through it. This surface does. So which is it? This is what Maxwell realized. This is a contradiction. This is inconsistent. We can't have it both ways. And our hands are really tied as far as this planar surface. Like the wire is definitely passing through it. Like Ampere's law is pretty unequivocal about there being some current passing through that surface. So Maxwell invents a fictitious, at least as far as he knew, current that is associated with the fact that the electric field is changing. there does, it has been since measured with more modern technology, that there is a magnetic field that exists between the plates, as if there were a current from one plate to the other. We are displacing charge from one spot to another and not letting it technically make a full circuit. So Maxwell says, all right, let's talk about a displacement current. Maxwell says a changing magnetic field produces an electric field. Got to be vice versa. A changing electric field produces a magnetic field. Got to be. That doesn't make any sense otherwise. At least that's what Maxwell says. If changing one creates the other, electric currents create fields. So changing an electric field changes the current, which changes the magnetic field. But changing the magnetic field changes the electric field. And we have this back and forth sort of inductive capacity, right? Like the ability to do this. If we consider the rate of change of electric flux, and in order to make the units turn out right, all we need is the permittivity. And we have the unit of amps. That there is an effective current that creates the magnetic field we can imagine. The magnetic field, in fact, is created purely by the changing electric field between the two plates. And this magnetic field has been measured. So this is a very real thing. We don't necessarily need to define it as a displacement current, but that was Maxwell's solution, and that's the solution we use here. There's sort of conduction current, I sub C, where there's actually a current passing through some sort of conductor. And then there's this other term that we can think of as effectively a current that's creating a magnetic field, but all it means is a changing electric field. Next week, we'll see why I'm so excited about that. Actually, will it be next week? No, it'll be, it actually won't be until the next module, now that I think about it. But here's a preview. If we consider Maxwell's equations, Maxwell's four equations, in a region where there are no charges or currents, empty space, vacuum. Gauss's law for electric fields evaluates to zero because there are no charges. Gauss's law for magnetic fields evaluates to zero anyway. Faraday's law is Faraday's law. Remember talking about the example with the loop was in that like magnetic jar, and then right at the end of that worked that example, the video tutor was like, this would happen even if there weren't a wire loop. There would still be a circular electric field induced by the changing magnetic flux. That's what this is saying. Even if there aren't wires or conductors or charges or currents or anything, there still is an electric field induced by a changing magnetic flux. And if we look back, if there aren't any currents, that's fine, but this term survives in the absence of sources, charges and currents. Because if we've got an electric field that changes, then we have a circulation, a magnetic circulation. A changing electric flux creates a magnetic field. A changing magnetic flux creates an electric field. This works even in empty space. And it is magical. I mean, it's not magic. It's real. It's science. But it's gonna feel magical. Because we're not done chasing down the consequences of Maxwell's synthesis and innovation, right? Realizing that that term, this one, is necessary to fully, hadn't been measured, wasn't going to be measured, was necessary to make everything sort of consistent logically. That has far-reaching consequences. I mean, yeah, I mean, I've already talked about how it like drove Einstein to work on relativity, but it's more than that. There are a couple slides left, but I'm just gonna leave them for you. The content is on the slides, and we can end a few minutes early. The other couple slides are about superconductivity. This is a superconductivity state for mercury. If mercury is cooled to about 4 Kelvin, it suddenly flatlines as far as resistivity. The internal resistance of cold mercury drops to 0. Not 0.1, 0. A current established in a superconductor will continue unabated permanently. Unless we use, I suppose, unless we use that current to do something, in which case we're transferring energy. The reason this looks like it does, this is magnetic field. This is the external magnetic field, I guess. So as the external magnetic field is a strange graph. But it's also, so this I think is the external magnetic field is what we're showing us here. But it's also true that the magnetic flux is excluded from the thing. The magnetic field lines no longer pass through the superconducting sample. And we call that the Meissner effect. This expulsion increases the magnetic field to either side because it bunches up the field lines to either side. And that bunching up means that we can actually levitate a thing. The Meissner effect makes a superconductor a perfect diamagnet. It will repel other magnets. Just all the time, every time, because the field inside of it, the magnetic field inside of it is zero, according to the Meissner effect. And so we get this superconductive levitation. If only it were practical. If we could use this at normal temperatures, the highest temperature superconductive threshold that I'm aware of is somewhere in like the 150 Kelvin neighborhood, which is hot compared to 5 Kelvin, but still really effing cold compared to like human life. So it's not anything. We're not going to be powering any trains with this anytime soon because we have to keep them so cold that we're not going to net any like benefit. We have to spend so much energy getting things cold enough to be superconductors, which helps explain why there's a bunch of active research in high temperature superconductors.